too?
Yeah, they asked me to record and put a YouTube.
Oh, so they are doing it for getting job purposes.
And it,
Okay, this is the last presentation of 2011 plan design. Okay, the project design of the plan the authors are Gafar Aziz, Nicholas Young, Gordon William, Samuel H. Cortes.
Good morning, ladies and gentlemen. My name is Nicholas Jones. I'm here with my associates Samuel Porter, Gordon Nguyen, and Gafar Aziz. We're here to talk to you about the current state of municipal solid waste management, as well as the possibilities for production of synthetic diesel from this municipal solid waste. As a brief overview, we'll start with the current state of municipal solid waste management in Canada, followed by the problem statement of what we hope to achieve with our project. From there, we'll talk about the options for the conversion of municipal solid waste into desired products, as well as the use of plasma gasification for the production of syngas, syngas being a mixture of carbon monoxide and hydrogen gas. From there, we'll talk about the use of filtered crop synthesis for the conversion of this syngas into diesel. To begin with, this is a landfill, and as you can see, it's not pretty. It is the most common method of waste disposal on Earth. Canada, for example, disposes over 90% of our waste using landfills. As you can see here in a landfill in Malaysia, they're associated with the production of this nasty brown leachate, where leachate is a liquid that's produced as a result of rainwater falling through the decomposing matter, collecting all kinds of toxic compounds, biological organisms, very nasty stuff. Quite unfortunately, the U.S. EPA has determined that it's not a matter of if a landfill will leak, it's a matter of when. All landfills will eventually leak, and all landfills will eventually allow this toxic brown substance to contaminate the surrounding environment. And here in Canada, we're doing the same thing. As you can see here in a landfill in Waterloo, we may be more presentable. As you can see here in a waste transfer facility in Edmonton, we may do it cleaner, more managed, or well managed, more organized, but we're doing the same thing. We're taking our garbage and putting it in a hole in the ground. Now, there are alternatives, for example, incineration. Incineration is the burning of waste to produce energy. Unfortunately, it's associated with a number of environmental hazards. For example, the production of dioxins, the production of greenhouse gases, the production of acid-rain precursors, and smog. As a result of these concerns, the construction of new incinerators was banned in 1991 by the NDPs. Although the ban was lifted in 1995 by the Progressive Conservatives, the ideology stuck, and as of today, there's only one operational incinerator for the handling of municipal solid waste in Ontario. It's located in Brampton, holds about 500 tons per day. Now, the issues surrounding incinerators can be epitomized by this one facility located in Port Arthur, Texas. It's run by Veolia, and quite unfortunately, this facility has been tasked with disposing of the VX nerve gas, which has been stockpiled through the Cold War. This compound that's so deadly and so toxic that a pinhead can kill is undergoing incomplete disposal at this facility. The VX nerve gas is actually being burned, and small concentrations are exiting the stack. So the problem is that no matter how hard you try with incineration, the undesirable compounds will leave your stack. Although there is a drive to reduce the amount of waste we're sending to landfill, and the programs, the green bin program, the blue bin program, have been designed to reduce the amount of waste which is going to landfill. Now this has quite a positive effect. In single-family homes, for example, we have 63% diversion from landfills. There's a lot of room for improvement in the multi-unit homes where we have 18% diversion from landfill, giving us a total of 47% diversion from landfill in 2010. All this is good, we can do better, and that's where our project comes in. See, the problem is that we currently view municipal solid waste as a burden, something that needs to be collected, hidden away, stuck under the carpet, and buried. This is a change. Instead, what we need to do is start viewing our municipal solid waste as a resource, something that we can take and from this produce a valuable and saleable product. And here comes our solution. It will be to take this municipal solid waste, 500 tons per day, and from this produce synthetic diesel. We'll be producing a synthetic crude oil with a high diesel fraction. We'll be running 24 hours a day, 7 days a week, year long, except for the necessary maintenance periods. And for the conversion of municipal solid
biological process is a process used in the production of biofuels. For example, ethanol. This can be produced through the fermentation of corn, beets, and sugarcane. Another prime example, methane. Through anaerobic digestion, we can, at further ways, we can produce methane. As you can see from the following example, the biomass feed is uniform. By that I mean homogeneous. Unfortunately, the municipal solid waste we're dealing with is extremely heterogeneous. It contains organic and inorganic waste and other possible harmful contaminants. For this reason, this process will not be ideal for our project. Which brings us to the next process, the extractive process. This is usually used in the removal of desirable compounds from plant materials. Example, we can extract linseed oil from flaxseed, peanut oil from peanuts. For the same reason as the biological process, this will not work due to the fact that, as you can see also from the example, the biomass feed is also homogeneous. Which brings us to our last and preferred option, the thermal treatment. The thermal treatment is a very versatile option in terms of having consistent product, regardless of the feed, whether it's homogeneous or heterogeneous. The type of thermal treatment we're talking about today is gasification. Gasification is a process whereby solid is either directly or indirectly for the purpose of vaporizing volatile content in the feed. The solid we'll be dealing with today will be the municipal solid waste, and the volatile components will be the syngas. The primary constituent of the syngas will be carbon monoxide and hydrogen gas. Now, to be talking about the different types of gasification, I call my colleague Mr. Samuel Poyer.
So the first type of gasification that we considered was the conventional steam gasification. These processes usually operate for around 600 to 1,000 degrees Celsius, and energy is supplied either directly or indirectly. The direct energy supply uses the partial combustion of a fuel, for example, natural gas or coal, and the indirect energy supply is an electric media through superheated carrier gas, in this case steam, which is then sent to the gasification vessel. Regardless of the method of energy supply, you can clearly see that an increasing temperature results in a larger production of syngas, which is the blue and gold lines there. Now, all conventional gasification processes require some form of pretreatment, and these usually focus around moisture content and particle size reduction, as these parameters will greatly affect the overall process efficiency. Depending on the degree of pretreatment, conventional gasification achieves conversion of the MSW to gaseous effluents in the range of about 60 to 90%, where 65% of the gaseous effluents are syngas, so stuff we're actually after. The 10 to 40% of the MSW that is not gasified remains as a solid charge that requires a significant amount of cold treatment before it can be disposed of. The second type is plasma gasification. And I'll start off by explaining that plasma is commonly conceived as the fourth state of matter that comes about when a very large amount of energy is supplied to the gas. This large amount of energy allows the electrons and nucleus of the gas molecule to actually
this process, this is very exothermic. The following equation denotes the Fischer-Tropsch synthesis. As can be seen here, the carbon number for crude oil with high diesel fraction is C12 to C18. Also, desired ratio of 2 hydrogens to 1 carbon is desired for long-chain hydrocarbons. The following video will demonstrate this phenomenon. The green represents the catalyst, the red represents the oxygen, the white represents the hydrogen, and the gray represents the carbon. As can be seen over here, the carbon monoxide molecule is dissociated via the catalyst. And then the free carbon atoms then form long-chain hydrocarbons right over here with the hydrogen atoms in the free. So as can be seen here, here's a long-chain hydrocarbon and it's forming over here. And they're quite long. So as I stated previously, there are impurities in high-temperature syngas, alluding to this quote over here. Currently, there are no technologies available to clean high-temperature syngas to meet the requirements of the Fischer-Tropsch synthesis, and this is by a professor in France at the University of Savoie as of May 2011. So one way we can address the cleaning of high-temperature syngas is to utilize the heat exchanger, in which we can decrease the temperature of the syngas. After that, we can use processes such as scrubbing and water quenching to remove the impurities that are not resided in the heat. As stated before earlier, these impurities can damage our catalyst. Therefore, these cleaning methods must be utilized. One of the methods that we most normally looked at is the two-stage dry scrubbing process by Westinghouse Power Corporations, also known as the ultra-clean syngas polishing process, in which a two-stage dry scrubbing process is utilized to decrease the concentrations of these impurities that damage the catalyst that we need. Also, water quenching can reduce other impurities such as ammonia. So now we must select the catalyst to facilitate the Fischer-Tropsch synthesis. We select the 3 catalysts to compare: ruthenium, iron, and cobalt. Ruthenium is an excellent catalyst, has excellent selectivity, and has excellent properties as a catalyst to produce crude oil with high diesel fraction. However, it costs $4,000 a kilogram, making it very cost prohibitive. Iron, on the other hand, is very inexpensive. However, it mainly produces C1 to C4 methane butane, which is not desirable for petroleum. Lastly, we will examine cobalt. We decided to select cobalt based on the following properties. Based on a report by Shell has reported that their cobalt catalyst has lasted up to 5 years. However, other companies such as Sasol have reported several thousand hours of usage. Also, this catalyst produces the correct amount of carbon number, C12 to C18, which is required for crude oil with a high diesel fraction. And lastly, it is moderately priced when compared to ruthenium. So now we can select a vessel to house the Fischer-Tropsch synthesis. We will compare this vessel based on 3 of the following qualities: the quantity of the hydrocarbons produced, the quality of the hydrocarbons produced, and the compatibilities of the catalyst. So here are the 4 vessels capable of housing the Fischer-Tropsch synthesis. To the left here we have a multi-tubular reactor. This reactor can have 2,000 up to 5,000 tubes in it. As can be seen by these numbers, these sheer numbers, it is very hard to remove the catalyst and change the catalyst with the sheer number of tubes. Another issue such as fouls and others can arise, making maintenance costs and capital costs extremely high and undesirable, making this vessel undesirable. Next, we have the circulating fluidized bed reactor. Again, low productivity, low capacity, not what we need for this project. This reactor was later replaced by the fixed fluidized bed reactor, which is commonly used in the industry today. However, with this reactor, it mainly works with iron. And iron, as I mentioned previously, produces C1 to C4 methane butane, not what we need for this project. Therefore, we have selected the slurry bubble column. So what is a slurry bubble column reactor? Well, the slurry bubble column reactor is a vessel in which there's a slurry inside the vessel with a catalyst suspended within it. And the gases bubble through from the bottom, making a 3-phase reactor, gas liquid solid. We decided to select this reactor for its favorable thermal efficiency, thermal superiority compared to the other vessels, because the Fischer-Tropsch synthesis reaction is very exothermic. With a submerged heat exchanger inside the vessel, this addresses the issue of hot spotting, because hot spotting can deactivate and destroy the catalyst required for the Fischer-Tropsch synthesis. Also, having the heat exchanger inside the vessel, inside the slurry, creates a uniform temperature. Also, this vessel takes smaller sized catalyst particles from 10 micrometers up to 200 micrometers. However, the desired number is 10 to 75 micrometers.
Very good.
Very good.
Yes.
We're very happy to hear.
I'm going to ask you a couple of questions. First is about the inconsistency about the feed. Because
Yes.
as you mentioned, the base you are going to get is going to have, every batch you are going to get have different composition.
Yes.
So how you are going to deal with that? Because it wasn't clear for me that are you going to have any in the pre-treatment stage, for example, to do separate some of the items from the waste, or how are you going to deal? Are you going to set everything?
For the thermal treatment options for all waste disposal techniques, there are the large objects, the mattresses and any kind of large couch that needs to be removed from the feed. There's going to be just a basic feeding system that will allow us to sort any large objects. But one of the benefits of using plasma gasification is that it allows us to handle a varying feed with varying composition, varying moisture content. It's very flexible in what it can handle. And that's one of the reasons why we chose it. It gives us consistent product with a consistent.
So any type of the waste will be fed to the system?
Yes, so we are looking at possibilities for moving any kind of magnetic materials for recycling, but we can handle the metals. They'll be vitrified in our plasma gasifier. One of the benefits of plasma gasification is that any non-volatile composition that can be gasified is actually sent as a molten product to it'll be a molten vitrified slag. We'll use a water quench to solidify it to actually sell the product. It's like $15 per ton as a construction aggregate. So we can actually, any items, any inorganic compounds, glasses, we can vitrify and sell as another source of profit, which is one of the benefits of plasma gasification.
So again, since we have the inconsistency, is it going to have any, is there any effect on the composition of the product you are going to get?
It will have an impact.
Intermediate products?
On the syngas composition will have an impact on the impurities as well as the ratio of the carbon dioxide to hydrogen gas. It will have an effect on that. We will be utilizing the water gas shift in the three-port region of our gasifier. It's the upper part of the gasifier which will allow us to adjust our hydrogen to carbon monoxide ratio. We're aiming for about a 2 to 1 ratio. But it will allow us to modify the composition with a varying feed composition. Any other questions?
Yes. So, you talked about the plasma technique.
Yes.
I expected to hear more about the nature and then the basic of the plasma technique. And then why, for example, you show a graph and then it shows that, for example, you are not going to get any CO2, almost negligible amount.
Yes.
So what happens inside the system?
Perhaps somebody else could answer the question, because not all the questions are covered. Casar, for example, or
CO2.
For example, why when you apply, what happens inside the system that you don't get CO2, and then almost you get everything is going to be CO and H2, which is the same.
The high temperatures of plasma gasification allow for almost 100% organic conversion to gaseous effluents, and these do include CO2. But above 800 degrees Celsius, through Boudard reaction, which is a molecule of carbon dioxide and carbon reacts to form 2 molecules of carbon monoxide.
at the numbers, you calculate, you are going to get to mention that it's very crude numbers, but the issue is look at the price. Plasma versus the conventional gasification is almost twice.
Yes.
Am I right? So how you are going to justify that, okay, you are going to go with plasma? So is it just based on this technique is more environmentally friendly, or how we are going to justify? Because it's a major issue.
Since we're looking to produce food with a high diesel fraction, we're looking for the process of liquid the most syngas, which then lets us produce the most hydrocarbon products. And plasma gasification by far produces higher quality and a higher quantity of syngas. The only drawback is that it is more expensive because we're using electricity to generate the plasma. So the only justification we need to make for what we thought to justify the use of plasma is that the additional syngas is worth the additional cost of the energy. So this slide simply serves to make that justification that the extra syngas we're getting is worth the extra electricity.
And as stated, we received more than double, almost double the amount of syngas with plasma gasification and energy conversion as gasification.
Thank you, very nice.
Did you get that idea that you don't need pre-treatment for plasma?
The number of plasma gasification waste destruction facilities that were coming up on the previous slide, or the subsequent slide, one of the things with plasma is they always stress in articles is that there's absolutely no pre-treatment required. That the moisture
Your
content...
project is for Toronto, right?
Sorry?
Your project is for Toronto.
Yes.
Okay. Just imagine what you have in Mason. You don't need pre-treatment.
No, it comes right off the truck, so it's not like we're getting couches and televisions. It's pre-shredded and pre-compressed.
So there's a pre-treatment.
Well, we're not doing any pre-treatment. Pre-treatment is done in the truck, so at collection of municipal solid waste. We wouldn't have to pay for it. Someone's doing
What do you do with the battery?
I'm sorry?
What do you do with the battery?
From it. I believe that they would end up as a part, either contributing to the acid gases that we need to clean up.
No, just a regular battery.
Alkaline battery.
I believe they'd be,
Or mercury battery.
they become a part of our electrolyzed slag. It's a non-leaching product that,
So you need pre-treatment. Because in Toronto there is no plant to separate the battery.
Sir, for the batteries, for the most part, most of our equipment was based on single-family homes and
Could you speak on the microphone?
most of our composition was based on for the single home and multiple homes. So for the single home, especially where we have the premium project and the premium project. So like basically what that does is that is we change the amount of batteries for the most part we can get for the composition that positively classified. And for the most part also like when the truck brings in the gas, it places it to the battery without which is making the compress, right? So instead of taking it to the battery, they bring it into us. So we just we throw that into the gasifier and the high temperature and everything will be treated.
So, this is something we should look into, but from my understanding is that the batteries, the actual metal encasing will contribute to our vitrified slag, and the acid inside will contribute to the acid gases that will need to be scrubbed out. But basically, we can just throw it in.
It's a good assumption.
Well, something that will have
Not
to
practical. Okay. Believe that cable for analysis, oxygen analysis. What is your liquid product?
It's a crude oil with a high diesel fraction. So we're
Get,
aiming to produce diesel, but we're going to get a very degree of hydrocarbon.
Will you get in conventional gasification also liquid product?
Yes.
this is after the...
This is after this is
Yeah.
the hydrocarbon products based on the amount of syngas. So it assumes selectivity and yield, but of course it's a terrible assumption, but as long as it's the same for the conventional amount of
You answered, terrible assumption.
the comparison. I mean, if it's only to compare, assume the same thing for both of them, the comparison should
And
be.
where you get that energy demand again?
That was based
Plasma
on,
is much more than double than
it was
conventional?
Well, it was actually a very crude assumption, but if we,
okay. No, what is, you said
is actually, the positive number is from literature, so the 3 million is based on, is not based on any assumptions. But for the conventional, we just assumed it was 50% of the price.
I think some of your numbers belongs to coal, some of your numbers belongs to plasma.
No,
And look at,
all
no,
of the, all of our what we took from literature was just plasma.
To take anything from literature is meaningless. From what literature? What paper?
The actual article.
That's right. From literature is almost a way of escaping the question. I took the numbers from the literature. Okay? That's easy to be attacked. See, I am attacking you because of that.
But if it's a similar plasma gasification waste destruction facility with a similar capacity of what we're looking at. So if they have the same capacity, they would probably use the same energy demands. So their energy demands, calculate that based on Canada's energy pricing. So we didn't take their energy costs, we just looked at their energy demand, calculate their own costs.
okay, just one more question. Can I see your flow sheet, please? Okay. Your reactor R1 is working at 1400 degrees centigrade?
We're not entirely sure of the exact temperature, but typical gasifier temperature is about 1500 degrees Celsius.
How much?
1500 degrees Celsius.
1500. And your material, the solid material or molten material is coming from the one at 1500 degrees centigrade. And you cool it with water?
Could you answer that, Gaffer?
Yes, sir.
Yes.
Is that your answer?
Sorry, the question was the solid coming out?
Yeah, the solid coming in at 1500 degrees centigrade.
Basically,
Actually, the molten material,
Huh?
molten material coming from your plasma gasifier
Yes.
is 1500 degrees centigrade.
I would assume so due to the fact
Or
that
it's cooler.
what happens, I would assume so due to the fact that the temperature that's already, that's why I assume to be 1500. 90% of this is gas and the 10% remaining is molten
No,
solid.
I'm just talking about the temperature. Temperature is 1500 degrees centigrade.
Yes, sir. Due to the fact that
And
it is 1500.
and you're cooling with water?
Sorry?
And you're cooling that heat exchanger with water?
Pretty much. Using the water pressure to verify the fact.
What will happen to the water? Let's assume you can do it. What will happen to the
What
water?
happens with the water is that we can generate steam from that, which we can also use around the procedure.
It becomes the steam?
Huh?
It becomes the steam or won't
It
become?
becomes all water. It becomes all water. So,
Oh, it's still hot water.
yeah.
Okay.
So well, for the most part, when it goes through the heat exchanger, we use that in the turbine, which also can be used for electricity in other parts of the plant.
Thank you.
What about cooling down with ice? You can go.
In essence,
You
right
can
now
go.
we're still in a very
You could call the ice cream guy and you bring a few cubes of ice and we put it here. But that's it. There are options. Okay, I have a few questions. Let me see, Gafar, one of the things I want to know. How do you find, well, first I have to make an announcement, but not very much of an announcement. 25 years ago, I worked in Ontario Hydro in plastic. Ontario Hydro had so much energy that they didn't know what to do with electrical power energy. So I worked in Evelyn Avenue here in Toronto. And they wanted to use electricity because, as I said, they didn't know what to do with it. So they bet that they could be producing gas. Now, the final conclusion was that it was not economically viable. It makes a lot of sense. You don't have to be a genius. You get a little bit into some material balance, and finally the whole cycle of the thermodynamic efficiency, you find that. So why, as I think it was Samuel, the one who was talking about the applications, why we are using plasma in the literature? I think it was, you were the one who was talking about the literature, is that right? Okay. So why the literature bothers to talk about plasma? Why? I'm going to tell you, because Gaffer is not going to answer. Are you going to answer, Gaffer?
Why we use plasma?
Why you have been reading plasma to obtain something which is not syngas. Okay, let's call it syngas from municipal waste. Why they present this plasma torch, plasma reactor?
We decided to go with that due to the fact that it has a very high conversion compared to the steel gas switch.
Is that right?
From basic research,
We're talking about friends. You can talk freely.
yes.
Is that what you're saying? Has a high thermal efficiency? Is it what you meant?
Well, I was saying that we have a higher conversion, and because we're dealing with higher temperature.
But high conversion of what? Into atoms of hydrogen, carbon, conversion into what?
High conversion of the municipal solid waste to syngas. You get more, you get the main primary constituent.
At what price? At what price? Assuming that what you say is right. Okay. You know when you can apply plasma? When it's highly toxic. A substance is highly toxic. And it's extremely difficult to handle that socially and socially acceptable. So the amount is small. The amount of hazardous waste is small. And then it's worthwhile to apply for that specific case. Otherwise, it's an exotic thing. Because you are using the best form of energy, electric power, the neatest, the best, into something that is garbage after all. Although the garbage can be partly recuperated, can be reused. Okay guys? So you have that. That can be used for only some, for example, highly dangerous chemicals used by the army. The armies, you know, they experiment with all kinds of very toxic compounds. Of these toxic compounds of mass destruction. Okay. So this is one of the things I wanted. I continue with that part. Tell me, how do you find the circulating fluidized bed that you discarded, guys? Guys, but let's go first with Gaffer. First I want to know how, why is discarded? Why do you discard that?
Why do we say that?
Yeah.
These are the four main types.
Talk too close to the microphone. Because I am a little deaf, you know. This is the problem of my life. I am a little deaf.
Well, from the four designs there, this one is cost prohibitive because we have like almost 2,000 to 5,000 tubes. So cleaning and clearing out the cabinets is cost efficient and also increase the maintenance time that we're trying to avoid. This one also which has been replaced by the fixed fluidized bed. As my colleague said earlier, this works mainly with iron, and iron can produce C2 to C4, which is not the ideal diesel fraction that we need. Which brings us to this one, the last one, the fixed storage bed.
No. I'm talking about circulating fluidized bed. Why you discard that one? Why don't you use, for example, the Sasol process? You know the Sasol process, where is it used, or when it was used, or from where it's coming? The Sasol process that you have there.
I didn't look much into it for the most part. As my colleague explained to me, this was later was improved. Improved technology was later used. This was fixed to that replaced.
replacement, you know. We are all replaced electrons, all of us. I am talking about why circulating fluidized bed, why you discard that, the circulating fluidized bed?
The circulating
No,
fluid.
no, 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 no.
I didn't look into it, so I cannot tell you something.
Okay. Let me see. You guys, you have been talking, all of you, about syngas. When you apply the specific case of plasma, that you can achieve very high temperatures, you mentioned, and this is theoretical, the syngas is okay when you are using, for example, as they use in South Africa. In South Africa, they use the Sasol process to circumvent the apartheid problem with oil. But anyway, that's history. When we have a time, we can have a coffee and talk a little more about it. But the thing is that the syngas that you are talking about contains highly toxic substances, including dioxins, high temperatures, NOx. So it's not just the H2 and CO. That's nice. As I said, it's very cute. It's very good in the movies, but it contains very corrosive and toxic substances that you have to go through other processes even to eliminate these byproducts. I am directing my questions to Gaffer. Okay.
Sir, from our previous researches, and due to the interpretation we're looking at, like I said earlier, gasification is a process whereby very organic waste into syngas. For this process, the waste materials are treated with high temperatures, with no combustion involved. With that alone, combustion means that there's very little or no oxygen. So that oxygen, the action of oxygen pretty much reduces the fact that we will have the absence of urine in the syngas components. And if there is, by any chance, it will be negligible. And if you look at it from here, even if there is, the fact that it's negligible, after the heat exchanger, when it goes through the first scrubbing process, it is reduced, and then at a cooler temperature, it is also reduced from the second scrubbing process.
What was the residence time that you expect in the circulating fluidized bed? What is the residence time for the
Residence time?
particles? Yes. What do you expect?
I honestly cannot say that at the moment.
Okay. A final question. Let me see one moment. I think I met you, any of you, I don't remember who was, that incineration was a no technology. Is that correct?
Incineration is no good?
I understood.
Yes, we agree.
You said that?
Yes.
Or I wanted to know if I interpreted that.
Yes, there are many environmental problems associated with incineration. One of the big problems is that no matter how hard one tries, the issue is that we cannot. Sorry, you cannot control what comes out of your stack. This facility here in Port Arthur has been tasked with disposing of the VX nerve gas, a very toxic, very deadly chemical. And unfortunately, no matter how hard they try to prevent it from leaving their stack, they are having small concentrations of this VX nerve gas exit their stack, even though it's highly problematic stuff.
Well, again, Japan is a country with very small surface, small land, cramped, socially just, a very high density. And in Japan, they use incineration, like they use it in Germany also, a country with a huge concentration of people. Do you think that they have not thought carefully about the consequences and the comparison between landfills, for example, and incineration, to see that incineration is a very good, is an acceptable option?
It's one of the things that Mr. Porter had commented on was that we're seeing a lot
closer to the microphone? I say that not because I am dead,
Yeah,
it's because I dare to say, speak for everybody.
sure. The morning